Okay. Today we will start with families of Gaussian stochastic variables. So Gaussian random variables. Let me start from the recalling what is the Gaussian distribution in one-dimensional and infinite dimensional space. So let psi is Gaussian random variable. If psi has a density of such kind, p of x is equal 1 over square root of 2 pi sigma e minus x minus a square divided sigma square. Here a and sigma are constant such that a is arbitrary real number, sigma is positive. This constant have a following meaning, that expectation of psi is equal to a, and variance of psi is equal to sigma square. So you see that Gaussian distribution in one-dimensional case is completely defined by its mean and variance. We will denote Gaussian distribution with parameters a and sigma square as n a sigma square. Sometimes it is called normal distribution due to its role which in the mathematical statistic and the central limit theorem, which we will mention in the future. For us, it will be good to have a characteristic function of the Gaussian random variable. So let us consider characteristic function of psi. This is the expectation psi t, the expectation of exponent e t psi, and now it also can be easily calculated. It is equal e t a minus t square sigma square over 2. So this is a characteristic function of Gaussian random variable. The interesting properties of Gaussian random variables begins when we consider the families of such variables. So the next definition is related to the Gaussian family of random variables. Definition. Suppose that we have a family of random variables, which is indexed by the index alpha, which belongs to some set A. This family is called a Gaussian family of random variables. If for all finite set of indices alpha n from A and all real numbers which belong to R, we have the following. The sum k equal 1 to n, ak psi alpha k is Gaussian random variable. Of course, when we have the definition of the new mathematical object, we have to look for examples of such object, and also we have to understand why it is so important to consider such object. So let me give you examples and motivation for considering of such families. Let us begin from the examples. Example. Let me take psi1, psi n, finite number of random variables with such properties. Suppose that they are independent and Gaussian random variables. Random variables. Then I claim that let me page that this finite set psi1, psi n is a Gaussian family. Let us check this. Let us check this. Suppose that psi k has a normal distribution. We use the notation which already introduced with the mean AK and variance sigma K square. K equal 1 to n. Then what we have to do? We just have to consider linear combination of our random variables with an arbitrary coefficients. This will be a sum from k equal 1 to n, for example, ck psi k. The question is whether it is a Gaussian random variable or not. How one can check this? Maybe you remember that we already have an expression for characteristic function of our random variable, of Gaussian random variable. Also, you know from the probability course that characteristic function uniquely defines a distribution of a random variable. So if we will be able to check that the characteristic function of our linear combination has this kind, then we will say that we prove our statement. Linear combination has a Gaussian distribution. So let us try to use characteristic function. Expectation of the exponent of the following sum, sum from k equal 1 to n. I will put here E, T, Ck, psi k is equal to. I take the multipliers imaginary unit and t from the definition of characteristic function inside of the sum in order to emphasize that here we have the sum of independent random variables, you see, because it is our condition. We have independent random variables. Due to this fact, one can say that the characteristic function is equal of the sum is equal to the product of the characteristic function. So now I can continue our calculations with the following formula. It will be equal to the product from k equal 1 to n. Here is expectation of the exponent of every summand. Here is E, T, C, K, Psi K. Now the calculations became to be very simple because this is just a characteristic function of the random variable psi k, which is calculated at such point. Yes, at such point. T multiplied to ck. So now let's apply the form of the characteristic function of the Gaussian random variable, and we will have the following. It is equal, here's exponent E T C K A K. It is AK is the mean of the random variable psi k minus T square ck square sigma k square, which is the variance of psi k, divided over 2. Now let's write it under the sign of one exponent, and we will have exponent of the following. Et multiply on the sum from k equal 1 to n. Here is ckak minus t square over 2 multiplied on the sum from k equal 1 to n ck square sigma k square. You see, we have here expression which is exactly coincide. Let me show you again. Which is exactly coincide with the characteristic function of Gaussian random variable. Even more, we know now the parameters of our distribution, so we obtain the characteristic function of normal distribution with the parameters sigma k1 and ck ak and sigma k equal 1 to n ck square sigma k square. Okay. By the way, here for people who like very rigorous statements, it must be noted that, of course, the sum, it can happen that ck are all equal to 0. And the sum, which represents the variance, can be 0. In this case, we say that we have degenerated but still Gaussian distribution with the 0 variance. Yeah. Okay. Okay. So we proved that our family of independent random variables is a Gaussian family. Of course, we can expand this example. Namely, if we consider now the following family, sum from k equal 1 to n uk psi k, where u1, un just arbitrary numbers from R, then this family is a Gaussian family. So instead of initial random variables psi1, psi n, I'm considering all its linear combinations. And it is trivial that it is now Gaussian family because the linear combination of linear combinations is still linear combinations, combination of initial psi1, psi n. So we have such an example. And let me write this example in more convenient way, because in our lectures we will use often the language from linear algebra and functional analysis. So, namely, let us denote psi vector is psi1, psi n, and then u is u1, un. They will became to be a vectors from Rn. I suppose that Rn is equipped with the usual scalar product. So our family looks like this is a family of products Xi U, where U belong to Rn. From this point of view, it is good to have a following definition. New definition. Definition. We will say that Xi is a Gaussian vector, Gaussian, a random vector. Vector in Rn if let me new page. If for any U from our space Rn, this scalar product psi U is a Gaussian random variable. You see that this definition, of course, is only reformulation of the previous. But here we have arbitrary family. Here we have arbitrary family of Gaussian of random variables. In our case, we just consider the finite number of random variables, but due to this, we have more familiar object. Because in probability theory, you studied random variables and then random vectors. So it is good to study Gaussian random vectors after Gaussian random variables. And the first one is the question, how looks like the parameters of distribution of Gaussian random vector? Because in the case when we have Gaussian random variable, we have a very simple description. Its density or its characteristic function depends only on two parameters, A and sigma square, and they have a very clear and simple probability meaning. A is a mean of our random variable, and sigma square is the variance of our random variable. So it is desirable to have something similar for Gaussian vectors. And it is true, and we will be able to do this. So let us introduce the objects which is related to this case. So let us characteristic of Gaussian random vector. Let us introduce the mean expectation of Xi. It is simply a vector organized from the expectations of the coordinates. And now we have to introduce something which will substitute the variance. And maybe you know from the probability theory that this is a covariance matrix. Covariance of psi is a matrix which consists of the following expectations. Xi I minus its expectation multiply on Xi j minus its expectation. So this is a matrix whose elements are covariances of the coordinates of our vector. So we have such a matrix. It occurs that these two objects substitute for us mean and variance in description of the Gaussian distribution in the multidimensional case. Namely, let us calculate the characteristic function of our random vector. You remember that characteristic function exactly as in the case of random variables. For random vectors, also define the distribution of the random vector uniquely. So I say that this is characteristic function of such kind. It now it depends on the vector valued argument and is defined like expectation of the exponent. Here is E multiply on the product psi u. We have to calculate this, and it is easy now due to the definition of Gaussian random vector. Let me recall you that from the definition of Gaussian random vector, let me do here the break, and then psi u is a Gaussian random variable. Is Gaussian random variable. So we know the answer, at least formally. It is equal to exponent. Here is e multiply. I can put here for a moment 1. So we have a Gaussian random variable. We have this is instead of t in definition of characteristic function. Put here 1, and then I can write the answer. So here we will have expectation of psi u, and we have the 1/2, and here is sigma variance of psi u. So to get the answer in the term of initial vector xi, we need to calculate these two objects. Let us start here. A of psi u, this is just expectation of this product psi u, and it is trivially equal to the product of xi multiply on u. Yes. Similarly, what is this? Sigma square of psi u is equal to variance of this random variable psi u and is equal to expectation. Here is uh, psi u minus expectation of psi u square. It's equal to, now I'm writing everything in the coordinate form, and you will see, please do it carefully, you will see that it will be a quadratic form with respect to u equal to the sum from ij equal 1 to n. Here is expectation of psi I minus expectation psi I psi j minus expectation of psi j multiply u I uj. Then we see that this is just quadratic form generated by the covariance matrix. And finally, we can write our characteristic functions as follows. We have that expectation of the exponent of e psi u is equal to uh, exponent. Here we have e expectation of psi multiply on u minus 1/2. And here is quadratic form generated by the covariance of psi, u, and u. Okay, so from this expression, you see that the distribution of Gaussian random vector also is uniquely defined by the mean and analog of variance, which is now covariance matrix of the vector u. And we know the form of this characteristic function. Of course, we have the new question arises here. Why I am starting from the characteristic function? Why not from density? And the reason is that now density exists not always. The existence of the density depends on the properties of covariance matrix of our random vector. But before to start to consider density, let us check the following. Properties. Suppose that we have uncorrelated coordinates of our random vector. Let us see what happened with, in this case, with the characteristic function. So let us consider the corollary. So we have, let psi be a Gaussian vector such that psi equal to Xi1 psi m and psi m plus 1 psi n. So I divide its coordinates onto two subsets. This is 1 and this is second. That for every I which belongs to 1 m and j which belongs to m plus 1 m plus 1 n, we have the following, that its covariance of the corresponding coordinates is equal to 0. So expectation of xi I minus xi, and here is xij minus xij is equal to 0. So we have uncorrelated sets of coordinates in our random vector. Then these two families are independent. Xi1, xim, and xim plus 1, xin are independent. How to check this? To check this, it is enough to check that the characteristic function of these two random vectors is a product of the corresponding characteristic functions. So use characteristic function. Use characteristic function. Namely, when we consider the expectation of the exponent of E, here is, let me write it as follows. Here is the sum from k equal 1 to m uk psi k plus E sum from j equal 1 equal m plus 1 to n vj xi j. Then accordingly to our previous consideration, it will be written as follows. It will be equal the exponent. Here we have to write the linear combination of expectations. So here it will be like sum from k equal 1 to m uk expectation of psi k plus E sum from j equal m plus 1 to n vj exi j, and minus what we have to write here. Let me recall you. We have to write here the following term. And now, due to our supposition, this covariance of xi has a special kind. Let me, for a moment, write it. Now, covariance of xi has the following kind. It is a so-called block matrix. Why? Here we have something, this is a covariance between first coordinates psi1 up to psi m. Here we have something which is the covariance between the last coordinates psi m plus 1 and up to psi n. But here we have 0 due to our assumption. Since the such structure, I can write the corresponding quadratic form also as a sum of two quadratic forms. Let's do it. So we have minus. Here we have a u 1/2 u and minus 1/2 of b v v. Since then, we see that this is exactly a product of two characteristic functions. Let us write. So we will have the product exponent of e sum from k equal 1 to m uk xik minus 1/2 of a u and multiply on the same expression exponent of e sum from k equal m plus 1 n vk xik minus 1/2 of b v v. This is the answer now, and we see that our statement is right. Okay. The families xi1, xim, and xim plus 1, xin are independent. It is good to memorize such statement as follows. In Gaussian family, uncorrelated random variables are independent. Now we are ready to write the density of Gaussian random vector, at least in some special case. Example of density of a Gaussian random vector. Random vector. Now I will consider a special kind of Gaussian random vector. Let psi be a random vector with independent normal variables with such parameters. You see, maybe you often meet in statistics the name of such special Gaussian distribution with parameters 0 and 1 as a standard normal or standard Gaussian distribution. We will follow to this name, and I will say that psi is standard Gaussian random vector. By the way, why it is Gaussian? Because it has Gaussian and independent coordinates. we already have seen, or excuse me, we already have seen that this in this case it is a Gaussian vector. Okay, and so this is a standard Gaussian vector. Psi is called by a standard Gaussian vector. So let us check its characteristics. Expectation of psi is equal to 0, and covariance of psi is equal to identity matrix. Yes. Here, E is identity matrix. Of course, we have to understand the properties of such a vector, especially we are interested in the existence of the density. But before to do this, let me show you very interesting property of this vector. Namely, it is its distribution is invariant under rotation. What I mean by the invariance, the following statement. This is like property. Of psi. Let U capital be an orthogonal matrix. In Rn. This means that U conjugated is exactly U minus 1. So the one can have such examples like a matrix of the symmetry in R2 with respect to main diagonal, or rotation in R2. Sometimes people even use the notion that U is generalized rotation in Rn. Due to its property, U keeps angles and length of vectors, angles between vectors and length of vectors. So it's like rotate the space as a rigid body. Okay. So if we have such a matrix, then consider new vector, U psi. It is a Gaussian vector. You remember, if we take a linear combination, we again have Gaussian family, a Gaussian vector. Let's calculate parameters. Now, E of U psi, of course, it is U of E psi, and it is 0. Secondly, covariance of U psi. To calculate covariance, we need to calculate the covariance between products of U psi on some vector and U psi on other vector. Please do it by your self. So we will have the following formula, which is, by the way, valid for any random vector, not only for Gaussian random vector. This is U. And since covariance of Xi is equal to identity, then we have here U conjugated multiply on U, and by the definition of orthogonal matrix, it is equal to identity again. You see a very nice property. The rotation of the standard Gaussian random vector is again standard Gaussian random vector. So it has the same distribution, and if it has density, then it has the same density. Now let us check that the density really exists. And one can easily check this due to the following property. Psi has independent coordinates. So coordinates of psi have density. And this density has the following kind. Psi k has density p of xk is equal to 1 over square root of 2 pi exponent minus xk square over 2. Now let's use the standard statement from the probability theory that in case that a random vector has independent coordinates which have density, then the random vector also has density equal to products of coordinate. So density of Xi is the following. P of x is equal the product from k equal 1 to n, 1 over square root of pi, and here is e minus xk square over 2, which is equal to 1 over square root of 2 pi in n power, and multiply on the exponent. Here we have minus norm of x squared over 2. Yes. This is Euclidean norm, which is square, which is exactly the sum of squares of coordinate. So you see here exactly the property that the density of our standard Gaussian vector is invariant under rotation. So I gave you an example of a Gaussian random vector and its density. As I promised you, we now have to check the motivation, why we consider such families. And next lecture tomorrow, I will give you such an example. For today, that's all. Thank you for attention. Maybe somebody have comments, please. Okay. If there are no any comments,